All right, friends, in 3.1 in Advanced Algebra 2 today, we refresh our memory on factoring. We should have done this before, back in Advanced Algebra 1. We did a little bit in Advanced Geometry, so kind of make it a little faster. It's just a good refresher. We're going to need this, though, man. The factoring is not going to go away. So this is what we did in Advanced Algebra 1. We called this the factoring cheat sheet. And the first thing you look for every single time when trying to factor a quadratic equation is if there's a greatest common factor. And then after that, if you've taken out a GCF, or maybe there isn't a GCF, you check, okay, is there 2 terms or 3 terms in this quadratic equation? If there's 2 terms, it could be a difference of squares, which we'll talk about what those are later. In 3 terms, we talked ourselves through the perfect square trinomial, if it's easy factoring, or if it's frowny face factoring. So first few examples, we're just going to go through the different types. I've even told you what they are in these. So these are examples of a GCF situation. Greatest common factor, so you can see we've got an equation here. We want them to be equal to 0, and the greatest common factor means take out the biggest number that's common to all the terms. It's like the reverse distributive property. As you can see, we check that at coefficients first. This guy's got a 5 and this is a 20. Well, the biggest number that goes into both of those evenly is a 5, so we're going to like undistribute the 5. And we look at the terms, and don't you see that this has some x's with it, and so does this. It also has x's with it. So you take out the smallest amount of x's. This is x squared. This is x to the first, and that's it. Now you just kind of divide. You take this 5x squared divided by 5x. The 5 divided by 5 is the 1. X squared divided by x is x. The minus comes down, and then the 20 divided by 5 is the 4, and the x divided by x is 1, so that is basically like disappears. And then you close up that quantity, and of course he's still equal to 0. And these two guys are really the exact same thing. They're just in different forms. This is in factored form. What makes this great now is you've got two dudes times each other equal in 0. You've got this 5x basically times this x minus 4 is a quantity equal in 0. We use the zero product property to solve that. When two guys multiply together to equal 0, at least one of those guys has to be 0. So you look at this green quantity and you say, what value of x would make this turn out to be 0? Well, if x equals 0, because 5 times 0 is 0. And then you look at the red quantity, and you realize what value of x would make that. Well, what minus 4 equals 0? That would be 4. And then there's our two possible solutions. We'll put those in a solution set, 0 and 4, and it doesn't matter what order you put those in. So let's do another GCF situation here. All of these are GCFs indicated now. So biggest number that goes into both of these, remember he's got to be equal to 0 first, so he is, and that would be a 4, and this has an x with it, and so does this, so you take out the smallest amount that you see, and now we do some nice dividing. That would give us an x plus 8x divided by 4x is 2, and that equals the 0. And now we use the zero product property. What value of x makes this guy 0? If x literally equaled 0, 4 times 0 would be 0. Or if x equaled negative 2, like negative 2 plus 2 would be 0. So there's our solutions. And then one more. The only difference on this guy is he's not equal to 0 first, so we got to get him equal to 0. So we'll subtract the 18x over, and now he's equal to 0, and now we can take out the GCF. Biggest number is a 6 and an x, and that would give us x minus a shui, still equals 0. Don't forget that. You can't leave that off. You got to keep it an equation until you solve. So x equals 0 or 3, and then we'll put those in DOS solution set. So GCF, that's the first thing to look for every single time when trying to solve a quadratic. If you think in this order, factoring is really not too shabby. The next thing I've got on this sheet is perfect square trinomials. That was probably the weirdest one when we did all our factoring back in the day. So I've got in this nice box right here at the top of your page, like what it is to be a perfect square trinomial. There's 3 things that has to happen. Number 1, the first term has to be a perfect square. So if you're looking at this guy, right, this is the special case where it doesn't even have to equal 0. But if you look at the first term over here, is that a perfect square? Well, we know our perfect squares pretty well by now, like 1, 4, 9, 16 number-wise. But if you look at the variable, if it's raised to an even exponent, he's a perfect square also. So 4x squared totally is a perfect square. What I say is, like, if you say yes to that, like you're asking yourself these 3 questions, go ahead and put his square root right here. It's like, what would be the 2 things that have to multiply together to be 4x squared? That would be 2x. So there's phase 1, check. Phase 2 is the last term a perfect square. That's talking about this guy. Main thing, make sure he's thinking positive, because if that was a negative, he's not a perfect square. So yes, 9 is a perfect square, so I'll put his square root right down here. Then you bring the sign from the middle down. This middle guy's sign comes on down right here. And you still got to check one more thing, though. It doesn't mean it's a perfect square trinomial until we check to see if this middle term, this 12x right here, is 12x twice the product of the square roots. Well, product means multiply these two things together. If you take 2x times 3, you get 6x. And then you want twice that. Twice 6x is 12x, so boom, all three phases got passed here. This was a perfect square trinomial, and I'd hope so, since that's in this section of the problems that we're trying to work on. But just kind of refreshing ourselves, so bring this square root down, bring this square root down, check, is this twice the product? Then throw this quantity squared around it, and it's still equal to 0. That's how perfect square trinomials factor, is they factor into this binomial squared. So we don't really get to use the square root the zero product property on this. We get rid of this big old quantity squared by square rooting both sides. And the square and the square root cancel each other out, and you're left with 2x plus 3 equals. You'd normally have a plus or minus over here, but when that's a 0, there's no such thing as positive 0 or negative 0, so we've got ourselves just plain old 0. And then we solve for x. 2x equals negative 3. X equals negative 3 halves. And then we just get our one solution in this situation. So let's try another one right here. Again, this is in the perfect square trinomial category. We're just refreshing our memory. Let's check the three steps. Is the first term a perfect square? You bet. 4x squared. Is the last term a perfect before x is the square root, my bad. So we take the square root of him, we put him right down below. Is the last term a perfect square? Yes, square root of him is a 5. Then the sign from the middle comes down, since that's a minus. And then we multiply these together and double it. That would give you negative 20x if you multiply them together. Double that, negative 40x. Isn't that what this is? So that means he's totally a perfect square trinomial. So he factors to be those square roots, quantity squared, and now he equals 0. And now, since we've just got this one quantity squared over here, we can square root both sides. Meow, 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 meow. And we'll get 4x minus 5 equals plus or minus 0, which there is no such thing, so we're just going to put 0. And then 4x equals 5. X equals 5 fourths. 5 fourths. Wow. And now check this guy out. This is the rare case that we did very, very little of these back in the day. It's like, notice this guy isn't equal to 0. Well, he doesn't have to be equal to 0 if this guy on the left side is a perfect square trinomial. So instead of subtracting the 11 over to get this equal to 0, let's just check to see if this entire left side of the equation is a perfect square trinomial. So 16x squared, you bet, his square root is 4x. Then check the last guy. Is he a perfect square? Yep, 1's a perfect square. And then bring the sign from the middle down. Is this middle term twice the product of these numbers? You better believe it. So he's going to be this quantity squared, but now he equals 11. Well, we still do the same concept. We're going to square root both sides to get rid of that quantity squared, because those will cancel. And you'll get 4x plus 1 equals, now you need plus or minus the square root of 11. Do not change that to a decimal. We're keeping these nice and exact, so plus or minus the square root of 11. And now we're just going to solve. So same way we've been solving equations forever. We're trying to get x by itself. Let's get rid of this plus 1. So we'll have 4x equals, to bring that plus 1 over, you're going to have a minus 1. And then you're just going to leave that plus or minus the square root of 11. And now all we got to do to solve for x is divide this whole stinking thing by 4. X equals negative 1 plus or minus the square root of 11 all over 4. And remember when we did quadratic formula way back in the day, you'd get answers that kind of look like this. We're just going to leave it like that. And if you want to put it in a set notation, you got two different answers, negative 1 plus the square root of 11 all over 4, and negative 1 minus the square root of 11 all over 4. There's your plus or minus situation. So honestly, the perfect square trinomials are the weird guys. Everything else we're probably pretty comfortable with, but perfect square trinomials, we need some more practice with those. Difference of squares, boy, we've been getting better and better at those as the years go by. So a difference of squares, that's when you've only got two terms. And let's talk ourselves through this cheat sheet. You first check to see if there's a GCF. And between a 4 and a 9, the biggest number that goes into both of those is a 1. This has some x's with it. This does not have some x's with it. So there is no GCF besides a 1. So since it only has two terms, we want to see if it's a difference. Difference means subtraction, so bing, 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 winner there, of perfect squares. So is 4x squared a perfect square? Yes. Is 9, forget about his sign for a second now, is 9 a perfect square? Yes. So all difference of squares will only have two terms in them, and they will always factor into conjugates of the square roots. So the square root of 4x squared is 2x, and the square root of 9 is 3, and conjugates means you're going to have the same quantity, exactly the same, except one of them is going to be a plus in the middle, and one of them is going to be a minus. Notice you put the square roots in each category, but you've got this plus over here and this minus over there, and of course he still equals 0. And now we can use the zero product property, and from back in the day you should remember how to solve these very quickly. It's the old opposite of this guy over that guy trick. So that since this is a 3, the opposite of him is a negative 3. Come on, pen. Over 2. Or opposite of this guy would be 3 over that guy, which would be 2. And you get your two different answers there. So we'll put them in a solution set. Let's do that again. First we check for GCF. Is there a GCF between 16 and 49? No, sir. Difference of squares. Yes, this is a difference, and these are both perfect squares. So conjugates of the square roots. What you can do if you're really not certain how, let me make that a little better, certain how this is going to get set up, is you could set up two blank quantities. You can put a plus here and a minus here. It doesn't matter. If one of them's got to be a plus, one of them's got to be a minus. Throw your square root of the 16x squared in the first position. Throw your square root of the 49 in the last position right there, and then we can use the zero product property. X will equal negative 7/4 or 7/4. And remember, if you have questions on stuff like this, please let me know. Going through this a little quick because we've done this before. You know, this should be something that rings a bell. Here, I want to get him equal to 0 first, so 121x squared minus 4 equals 0. And now, two terms, no GCF. He's got to be a difference of squares, so difference, and these are perfect squares, so winner, winner, chicken dinner. They factor into conjugates of the square roots, so 11x plus 2 and 11x minus 2 equals 0. And x would equal negative 2/11 or positive 2/11. And solution set. Doesn't matter what order you have these two solutions in, they just both got to be in there. So difference of squares. And then the most popular one, the one that we were probably the best at, this easy factoring. Here's when you can do easy factoring. First, again, you check for a GCF. Then you see if he's a perfect square trinomial. And if that fails, then you got to check to see if you either easy factor it or frowny face factor. When can you easy factor? When the a value is 1. Remember, ax squared minus b or plus bx plus c equals 0. The a value is this number. So when he's 1, we're in a good situation. But let's realize why this guy's not a perfect square trinomial. Again, GCF between a 1, a 7, and a 12, not taking a GCF. This has x's, this has x's, no x's, so there's no GCF. Is the first term a perfect square? Well, yeah. X squared is a perfect square. Is the last term a perfect square? Negative 12 is not a perfect square. 1, 4, 9, 16, etc. 12 is not a perfect square. So we want to try to easy factor it. That's again where you find two numbers that multiply together to be this guy, C, and add together to be this guy. And the real trick to it is thinking about their signs first. Those two numbers could either both be positive, they could both be negative, or like one of them's positive and one of them's negative. This is the only three combinations. So let's realize this. If these two numbers have to multiply together to be a positive 12, there is no way that this is happening. There's no way that one of them is positive and one of them is negative, because a positive times a negative is totally a negative number, so it can't be that. The signs have to be the same, either both positive or both negative. Well, how do you figure out the other part? It's what they're supposed to add together to be. They're supposed to add together to be a negative 7. So is it possible for a positive number and another positive number to add together to be a negative 7? So these numbers both have to be negative. So you could make yourself a list of multiples of 12, and both of them are negative. Start with 1 and 12, both negative. Those do not add together. 2 and 6, both negative. Those do not add together to be a negative 7. 3 and 4, both negative. Winner, chicken dinner. And you could do this list mentally at this stage of your algebra life. What I do want you to put, though, is when you find the two numbers, the negative 3 and negative 4, so let's pretend I just kind of did that mentally instead of writing it down. I want you to write them down, like right here off to the side. Negative 3, negative 4. And then we factor that to be whatever the variable is. He's going to be a x. He's going to lead off both parentheses. So it's going to kind of be like this situation, equals 0. And then we just put those two numbers in here. One of those numbers was a negative 3. One of those numbers was a negative 4. So we put them in there. And now we use the zero product property, because we got two dudes times each other equaling 0, to solve x could equal 3 or 4. And if you need help easy factoring, I would be happy to help you if you come see me. Otherwise, I'm going to kind of just speed through this, because I hope that we know what we're doing. But let's realize we got to check for GCF first. No GCF. Wonder if this is, since this has 3 terms, I'd really like to check see if it's a perfect square trinomial. Hey, that's a perfect square. So his square root is x. That's a perfect square. His square root of 4 is his square root is 4. Excuse me. Bring the sign from the middle down. Is this term right here twice the product of those? Nope. I would need an 8x there, and that's a 10x. So this is not a perfect square trinomial. Maybe he's easy factor, and well, the a value's got to be 1, which he is. So I want to try to find two numbers that multiply together to be 16. So let's think about their signs right now. One of them, they have to be the same. They're either both positive or both negative. They can't be different signs. And then since they have to add together to be a positive also, they both have to be positive numbers. So 1 and 16, no. 2 and 8, there's our winner right there. So that's going to be x plus 2 times x plus 8. Keep it equal to 0, and then use the zero product property to solve. What value of x makes that 0? Negative 2. Or negative 8. One more. No GCF. Not a perfect square trinomial, because that's a negative 20 right there. So two numbers that multiply together to be a negative 20. That tells you right away that their signs have to be different. One of them is positive and one of them is negative. And adds together to be a negative 1. So the hardest part about factoring really is finding those two numbers. If you're stuck, make yourself a list. Do 1 and 20. And one of them is negative, so there's no way that those add together to be negative 1. 2 and 10, if one of them was negative, they wouldn't add together to be negative 1. 3 does not go into 20. 4 and 5, hey, we're close there. If one of those was negative, have to be. Which one is our bingo numbers? This guy right here, because those multiply together to be negative 20 and add together to be negative 1. So this will factor to be x plus 4 times x minus 5, because the 4 was positive and the x was negative, equals 0. And then x equals negative 4 or positive 5. Solution set. Sweet. Easy factoring. A value was 1. So here on the last ones, we finally have to frowny face factor. We got to always check things, though. If there's a GCF, we'll take that out. It's definitely not a difference of squares, because it's got 3 terms. Different squares only have 2 terms. Perfect square trinomial, no way. Easy, can't be, because the a value is not 1. It's something other than 1. So, to frowny face, I literally like to draw this little frowny face that tells me I need to multiply a times c, and that would be a negative 8. And now my job is to find two numbers that multiply together to be negative 8. And and add together to be this negative 7 right here. Well, since they multiply together to be negative, I know the sign, at least one of them has to be negative. Sorry, one's negative, one's positive. Then these two numbers right here, bing, they add together to be negative 7, so they're my bingo numbers. Now we take these four terms, or we're going to split this guy into four terms. First guy leads off. There's that 2x squared. Then the two numbers that we found next, they come, and really it doesn't matter what order they go in, but if one of them is negative, it's a good idea to put that one first and the positive one second with the variable next to them. And then the last term, that minus 4, he comes down, and we of course have to keep it equal to 0. Then we double group, make these first two terms into a group, make these last two terms into a group, keep that plus outside, and then we take the GCF out of each group. So 2 goes into each one of these as a number, and x goes into each one of these as the smallest guy. What we're left with, 2x squared divided by 2x would give you 1x. Then the minus comes down, and then a divided by 2 is a 4, and x divided by x is 1, so that's gone. And then whatever this sign is, that's the sign of the GCF that's coming out, so it's going to be a positive. Well, between a 1 and a 4, there's just a 1, and this has x's and that doesn't have x's. So you got to take out a GCF, and in this case, that GCF is a 1. And if your memory serves you well, whatever's in this quantity right here has to be the exact same thing in this quantity for this to factor correctly. So I should have got that x minus 4 both times. Now the last move is to regroup. So these green GCFs, they're going to become a group of their own. So the GCFs become a group of their own, and that common group of x minus 4, because he was common to both of those terms, comes down for the ride, and he's still equal to 0. And now we solve x equals opposite of this guy over that guy, negative 1/2, or 4 in this situation. So we put her in the solution set. Let's do that again. Definitely check for GCF first, and there is no GCF, not a perfect square trinomial, can't easy, so it's got to be a frowny face, and that's a negative 6 when you multiply those together. And two numbers that multiply together to be negative 6, add together to be negative 5, 1 and 6, and of course one of them has to be negative. So split it into four guys. The 2x squared comes down. I like to put the minus guy next, and then the plus guy over meow, and then minus shui equals 0. Double group. These guys become a group. Those guys become a group. Take the GCF out of each group. So 2x is the GCF here. And then we'd be left with an x minus 3. Here the sign is a plus, so that's the type of GCF I have to factor out. Again, we're only factoring out a 1. And you got to be left with x minus 3, and we are left with x minus 3. Regroup these GCFs that we took out, become a group of their own, 2x plus 1, and then x minus shui, and that equals 0. X equals negative 1/2 or 3 solution set. There we go. Next guy. Oh, check it out. First thing I see is if there's a GCF, well, even, I totally know that I can take a GCF out. So look at the smallest number in there. It's a 4. Does 4 go into all these other numbers? Nah, 4 doesn't go into 18, but 2 will definitely go into each one. So let's factor out a 2, and now we're left with 9n squared plus 9n plus 2. That equals 0, and that was nice. And now, let's see, we're looking at the red guy only now, if he can factor further. He's not a perfect square trinomial, even though the first guy's a perfect square. The last guy is not a perfect square. So it's time to frowny face because the a value is not 1. So those multiply together to be an 18. And I need to find two numbers that multiply together to be an 18 and add together to be a 9. So the signs have to be the same because this is positive, and since this is positive, they're both positive situations. So 1 and 18, no. 2 and 9 do not add together to be 9. 3 and 6, though, there's a winner. So Mr. Blue 2, that GCF we took out, he comes down for the ride. And now I'm going to split this red guy into 4 terms. the 9n squared. Since they're both positive, it really doesn't matter what order you're putting these guys in. Two numbers that we found were 3 and 6. Sorry, I was thinking that and wrote 3, 6. And plus 2. And that still equals 0. And then you double group. The weird thing is just that blue 2 is just going to keep coming down for the ride. The whole process is the same though. So Mr. Blue 2, he comes down. And then let's take the GCF out of this first group right here. That'd be a 3n. And I'd be left with 9n squared divided by 3n is 3n. Plus 3n divided by 3n is Juan. So we'll put him. Again, this is a positive number right here in this third position, so we'll take out a positive GCF. And numbers that go into 6 and 2, the GCF to that is 2. And that's it. So I should get a 3n plus 1 back when I take 6n plus 2 divided by 2. And I will. Hooray. Close that blue parenthesis up, and it's still equal to 0. And now we regroup. Mr. Blue 2 is still there. Red GCFs become a group of their own. And 3n plus 1, that common group comes down for the ride. And now I use the zero product property to solve. There's actually 3 guys times each other. I got Mr. Green, Mr. Red, and Mr. Blue. Mr. Blue doesn't matter though because he doesn't have any variables with it. So you only care about the ones that have variables in it. So in the red guy, n could equal opposite of this guy over that guy, negative 2/3, or opposite of this guy over that guy, negative 1/3. And then you put those in a solution set. So one more frowny face, and notice what's different about him is he's not equal to 0. We want to get him equal to 0. So here's the 8x squared. Got all my x squares taken care of. I need to move this 7x over by subtracting. So since there's already 5x's over there, and I'm going to take away 7x, that'd be negative 2x. And this 3 needs to get moved over to the other side of the equal sign also. From here, I'll let you talk yourself through it. I would like you to pause the video and give this one a try on your own and check back with me. Alright, so it was a frowny face. There was no GCF to take out either. So two numbers that multiply together would be negative 24, add together to be negative 2, or 4 and negative 6. And then I split it into 4 terms. These two guys in the middle, really doesn't matter what order you put them in, but did that. Double group and take the GCF out of each group. And now a regroup. The GCFs become a group of their own, common group, and solve with the zero product property. Negative 1/2 or 3/4. Alright, so now it's all mixed up and I'm not telling you what to do. So they just say factor these, talk yourself through the factoring cheat sheet. So let's do that. Here's a quadratic equation. He's already equal to 0. First thing I check is GCF. 3, 24, 36. Well, you bet that 3 goes in all of those. So let's check x's. This has x's, this has x's, this does not, so I cannot take out a common factor of x, but that'll give me an x squared plus an 8x plus a 12, and that's still equal to 0. And now I check the red guy, right? So I've taken the GCF out. Well, maybe we can still go further. So the red guy, perfect square trinomial, maybe that's a perfect square. That is not a perfect square. Easy factoring, winner, is 1. So we'll keep that green 3 coming down, and our job now is to find two numbers that multiply together to be 12 and add together to be 8. So that would be a 2 and a 6. So this is really x plus a 2 times x plus a 6, and he's equal to 0. And now, since he's factored, we use the zero product property. This homeboy doesn't matter because he doesn't have an x with him. This guy, the value of x that makes that 0 would be if x was negative 2, or if x was negative 6 would make that guy 0. So winner, did a little GCF, and then we got some easy factoring. Next guy, holy cow, 100. This is the total advantage of talking yourself through the factoring cheat sheet. GCF, if you try a 9, it won't go in there. 3 won't go into all these terms. So there is no GCF that I could take out. Since there are 3 terms possible, the first thing to check for, well, is a perfect square trinomial. So let's see, is the first term a perfect square? Yes. 100x squared, square root is 10x. Is the last term a perfect square? Well, yes. that'd be a 3. Bring the sign from the middle on down. Is this middle term twice the product of these roots right here? So if you multiply those together, you get 30x times 2 is 60x. We've got a winner. I would hate to have frowny faced that thing, man. That's a lot of work. Perfect square trinomial. Now I can square root both sides. Those cancel right there, and you're left with 10x plus 3 equals plus or minus 0, which is just 0 either time. And then 10x equals negative 3. X equals negative 3/10. Oh, I love you, factoring cheat sheet to tell me what to do. You need to memorize that, by the way. You won't have that in front of you. Let's talk ourselves through the factoring cheat sheet here. Is this a difference of, is this a GCF? Do we have a GCF? No. There's only two terms, so it's either GCF or difference of squares. And since we've already taken out GCF, it's got to be a difference of squares. So that's a perfect square. That's a perfect square, and that's a difference. That's a difference of perfect squares. So that factors into conjugates of the square roots. Minus, one of them's a plus, one of them's a minus, equals 0. 0 product property, x equals negative 6/5 or 6/5. And that was a nice one. And the last one here is the one that gets messed up the most. I don't know why, but it does. It's like people automatically think that this has got to be a difference of squares. Just because there's two terms, it does not have to be a difference of squares. Check me out, man. The first thing on the list is GCF. Between a 7 and a 21, doesn't 7 go into both of those guys? This has got x's with him. So does that. So we can take out the smaller amount that we see, and that's a 7x. We're like undistributing right there. So now we just divide, and that would give me an x minus 3, and that still equals 0. And that's it, man. It's Mr. GCF. Now, 0 product property, because you got two dudes times each other equals 0. He matters. He's got an x. All right, check out that x. So that matters. What value of x would make that 0? If x was 0. Or, what value of x would make that 0? Oh, sweet. That's not a 3. 3. So, solution set, 0, 3, baby. All right, man. Let us know if you have questions. Have a good one.